This is the pre-lab activity for activity 13. This is actually a pretty critical activity. If we were on campus, I would stress over and over how this is the last meeting before experiment 7, the big experiment. So there's still a lot going on. There's a experiment 5 post-lab out there. There's an experiment 6 post-lab out there. So you've got things out there. That's experiment 5, experiment 6. These are things, come see me during office hours. Happy to go over. We can talk about, work through exam 2 you took. That'll take some time to get back to you. But what I really want to focus on for this video and this activity is it leads into experiment 7. Okay, experiment 7 is the evaluative report. That's the big one. It's worth 100 points. The skills you've already been, seeing and actually thinking about are now kind of put together in one big experiment. There is still opportunity to withdraw, so see me if you want to talk about that. If we're on campus, here's what I'd be talking about: the policies for experiment 7. Okay, so if you were on campus, it would just be you and your partner working on this. What does that mean? Well, that means you wouldn't be talking to any other groups, okay? We want you to problem solve. We want you to work as a team on a difficult experiment and address the issues with that and come out with good results. That's what we hope for you. So there'd be no talking to other groups. You wouldn't be going outside. You wouldn't be, talking with other people. That way you would be focused with you and your partner. This also means on campus, I would provide very little assistance. Okay, so I wouldn't, answer questions about the lab. I wouldn't, if you think, well, maybe I should do this. What do you think? I would say it's your choice. This is your lab. So this is still going to be the case. You'll have very little assistance from me once experiment 7 starts. Again, you can come to office hours. You can do whatever, and we can talk about things. But as far as actually experiment 7, I'll say you have to decide. I'll refer you. I'll say go back to activity 13 or go back to activity 7, but I'm not going to answer questions because I want you to be able to address some of these complicated things. 10% is on accuracy and precision. So, of course, if you're doing the experiment, you have to do it right. Well, the numbers that I've provided for you, that will have good accuracy and precision, so you just have to do good calculations. And the calculations aren't trivial. There's a lot to work through, and that's what this activity helps with. So spectrophotometry, that was first seen in experiment 3 with the nanoparticles, but now we're seeing experiment 7. So page 171 has a good background on the theory of this. You're going to use this equation today in the activity, so we'll talk about that equation here shortly. Again, the idea is thinking about experiment 7. So experiment 7 is going to involve the SpectraVis Plus. Experiment 7 is going to involve making a calibration curve. Okay, a big part of it was making solutions. So if you're on campus, you had to decide what concentrations do I want to make and how am I going to make those? Is it independent? Is it serial dilution? Can I make correct concentrations? And then make a calibration curve. Then another technique, again, that was just talked about last experiment, is then titrations. So titrations were in experiment 6. The hope is that you're on campus developing the skills, and then experiment 7, really applying those skills to a complex system. So again, 13 is really about gearing you up for experiment 7. So see me in office hours. We can talk all about activity 13 for sure, but then once experiment 7 comes, very little assistance. You do have 2 full days to work on experiment 7 down here, so you will have enough time to complete this. So today in activity 13, what you'll be looking at is the equation A equals ABC. Okay, well, where does this come from? Okay, remember SpectraVis Plus, this data that you collect is absorbance versus wavelength. Okay, and that looks something like this. And if you have several solutions, okay, it can look something like that. So that was in experiment 3, nanoparticles, and activity 7 is where you saw the SpectraVis Plus. So what this is saying then is this capital A is absorbance. Okay, so that's talking about how much light is absorbed by the sample. So that's our absorbance. And this is equal to this A, which is the molar absorptivity constant. Okay, and that's a mouthful, but the takeaway is it's a constant. And B, the next one is B, and this is the path length. Okay, so this is what you're keeping the solution in. Typically, we use 1 centimeter path lengths, but in graduate school, I had path lengths that varied significantly. You could try a variety of things, but usually this is 1 centimeter. Okay, so 1 centimeter path length. And then this last C is concentration. Okay, so concentration varies, but usually in this chapter, in this topic, we'll see it in molarity. So that's the equation. That's what goes in. Okay, so the constant, the path length is in centimeters, concentrations in molarity, and you're going to be asked about units. Okay, so I'm emphasizing here that's path length, distance, centimeters, concentration, molarity, and then you'll see what these units are of the constant and of absorbance. What I want to emphasize is when we looked for this, we would normally try and look at lambda max, or maybe in some cases if that was too high, we'd look at a lower, smaller maximum of absorbance. So what I'm pointing out here is this is the absorbance. Okay, that's the absorbance at this wavelength. Okay, so you can do this equation and you can say it's at 500 nanometers. Okay, so there's two questions in here that get confusing because you're given wavelength. What I want to emphasize is that this 500 nanometers is the wavelength. That's the title of your graph, or that's the understanding of where the equation's going on. 500 nanometers does not go anywhere in this equation. Absorbance equals A, B, C. That's just identifying the wavelength where this absorbance was taken. Okay, so that's one equation you'll use, and you'll look at that in a couple of different ways. The next equation I want to point out, this is actually how we used to measure absorbance, and it's called transmittance. And this equation looks a little complicated, but what I want to point out is on your calculator, 10 to the x and log are usually on the same button. They're functions of each other, so you might have log x and then second function's 10 to the x. So what this means is 10 to the x cancels out the log. Okay, so if you have %t and you're solving for a, you can just plug that in, %t divided by 100, negative log of that. However, if you have absorbance and you need to solve for %t, then you just need to know that 10 to the a and then 10 to the minus log, that cancels log, and you could actually move the negative over here if you want, it doesn't matter. So I'll do that, 10 to the minus a, so this is now positive. I just want to show you that 10 and log are inverse function, so that actually go away, that cancel out, and it would be left with %t over 100 equals this 10 to the minus a here. So that's another equation that you're going to rearrange and use in this activity. So the solutions are really refer you back to activity 7. That's where solutions were talked about being made. Do you do that by serial dilution? Do you do that by independent concentration? Experiment 7 is all about making solutions and then testing them with this absorbance versus wavelength. Okay, so I've got Now 3 solutions on here. They're going to have the same shape, just different height to represent. You see this equation. The absorbance is proportional to concentration. So the higher absorbance goes with the most concentrated solution. If you have a very low concentration, it's going to have a very low absorbance. So that's the data, okay? So this is the data, absorbance versus wavelength. The calibration curve is how you process the data, okay? So you've got a couple of problems on here. To help this processing the data, you need to graph the calibration curves. Our axis, in this case, it's going to be absorbance, okay? So that's not new. But it's going to look different because it's going against concentration. Okay, so let's talk about this. Again, let's just go over here to the left, and I'll pick this new area. So now I'm going to say this wavelength is at 375 nanometers. Okay, so what I'm doing is labeling my graph. This is absorbance versus concentration at 375 nanometers. So I would read the absorbance value here, 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 and here. So now I've got absorbance of those 5 points. And then I have to calculate concentration. It depends, okay? If you did independent, that means you take the grams, you go to moles, and you go to molarity. If it's serial dilution, of course, that dilution equation should just come to you right away. That's the MV equation. So M1, V1, M2, V2 dilution. So those are your 2 ways to calculate your concentrations. So now you've got your points, absorbance and concentration. Should be a nice linear relationship. And then you've got your curve for your standard solutions. Okay, so you saw, as you will see in the activity, that you're not done. And as experiment 7 comes, you're not done, because then you're given an unknown, and you have this for the unknown. Okay, so that means you know the absorbance. So now you can plug in some number. Let's say it was 0.543. You know the absorbance, and the equation comes out and gives you the slope and the y-intercept. So now you can solve for x, and what's x? That's the concentration of the unknown. That's what you're looking for. So this, like I said, this activity is an excellent preview for experiment 7. So come see me during office hours. Let's talk about activity 13.